In Unit 3, we're going to study the concepts of derivatives. In Section 3.1, we're going to look at the derivative of a function. Last unit, we learned how to find the slope of a tangent line using the formula m equals the limit as h approaches 0 of f of x plus h minus f of x all over h. This slope is known as the instantaneous rate change of a function at a particular point. It can also be referred to as the definition of a derivative. So the definition of a derivative, so instead of writing m, we can write f prime. And f prime means derivative is equal to that same limit as h approaches 0 of f of x plus h minus f of x all divided by h. A function that is differentiable at every point of its domain is called a differentiable function. So in this example, we're asked to find the derivative of f of x equals x squared. So now to find f prime, this is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is going to be the limit as h approaches 0. So in x, I'm going to replace it with x plus h. So it's going to be x plus h squared minus the function, which is x squared, and this is all divisible by h. So this is going to be the limit as h approaches 0 of x squared plus 2xh plus h squared. So when I expand this binomial, I get this trinomial. I'm still subtracting x squared, and this is all over h. So now anything that doesn't have an h should cancel out, and it does. So I'm left with the limit as h approaches 0. I'm going to factor in h out of my two remaining terms, and I'll be left with a 2x plus h over h. Now my h's cancel. And now I can substitute in 0 for h, and I'm left with 2x plus 0, which is equal to 2x. So therefore, my derivative, f prime of x, is equal to 2x. So basically, this equation represents the slope of any tangent line on the curve x squared. So if I wanted to find the slope of the tangent line when x is 3 on the curve x squared, I would just type in 3 for x here, and 2 times 3 would be 6. So this notation, say f prime of 3 equaling 2 times 3 equaling 6, means that on the function x squared, the slope of the tangent line when x is 3 is equal to 6. There's also an alternative formula for finding the derivative of a function at a specific point, say at x equals a. And this formula is f prime of a is equal to the limit as x approaches a of f of x minus f of a, all divided by x minus a. So let's take a look at an example of the second formula. So say we're asked to find the derivative of f of x, which is equal to x squared minus 3x at the point x equals 4. So in this particular case, to find f prime at 4, this is going to be the limit as x approaches 4 of f of x minus f of 4 all over x minus 4. Which is going to be the limit as x approaches 4 of x squared minus 3x, that's my function, minus f of 4 is really just the function evaluated at 4. So if I put 4 in here, I'm going to get 16 minus 12, which is going to be 4. And this is all over x minus 4. And now we're just back to evaluating limits from last chapter. The numerator factors into x minus 4, x plus 1 over x minus 4. Now my x minus 4's cancel. Now I can plug a 4 in for x. So the slope of the tangent line at x equals 4 of the function x squared minus 3x is going to be equal to 5. So again, some people might find this second formula easier to find the derivative at a point. Now, there are many different notations for derivative. There's y prime, there's dy, the derivative of y with respect to x. There's the derivative of the function with respect to x. And this is read as the derivative of f at x. And these all mean the same thing, and we'll use them interchangeably throughout the course. Now, one-sided derivatives. A function is differentiable on a closed interval a to b if it has a derivative at every interior point on the interval. So if the derivative from the right-hand side equals the derivative of the left-hand side, and it also exists that there's a derivative at the one side on the endpoints, then it's differentiable everywhere. Let's take a look at the one-sided derivative here. And we're asked to determine if the following function has a derivative at x equals 0. Well, before we can determine whether it has a derivative at x equals 0, we have to show it's first continuous at x equals 0. So first of all, we want to find out what the function at 0 is. And I would use the top equation to do that. So this would be 0 squared, which is 0. And then I would have to see if there's a limit as x approaches 0. And because it's a piecewise function and it splits at 0, I have to compare the limit from the right of 0 and the limit from the left of 0. So from the right of 0, I'm using this function. From the left of 0, I'm using that function. If I plug 0 in, this is going to be 0. If I plug 0 in, this is 0. So yes, there is a limit. The limit as x approaches 0 is 0. And since the value of the function at 0 is equal to the limit as x approaches 0 of the function, and they both happen to equal 0, so therefore my function is continuous at x equals 0. So now that we know it's continuous, we can try to see if it's differentiable. Okay, so now we have to show that the derivative coming from the right of 0 is equal to the derivative coming from the left of 0. So let's first of all find the limit as x approaches 0 from the right of f of 0 plus h minus f of 0 over h. So coming from the right of 0 is bigger than 0. I'm going to use this function in this calculation. This is going to be the limit as x approaches 0 from the right of 2 times 0 plus h. F of 0, I plug into here, and that's going to be 0, and this is all over h. And if I simplify this, this is going to be the limit as x approaches 0 from the right of 2h over h, and the h's cancel, so that limit is going to be 2. Now let's take a look at the limit as x approaches 0 from the left-hand side of f of 0 plus h minus f of 0 over h. This is going to equal the limit as x approaches 0 from the left. So I'm going to have to use the x squared function when I evaluate this part of my definition of a derivative. So it's going to be 0 plus h squared. Again, f of 0 is still 0 over h. So this ends up being the limit as x approaches 0 from the left of h squared over h, which is going to be h. And if I plug 0 in, I get 0. So therefore, the derivative from the right of my function was 2, and from the left it was 0. So therefore, the function is not differentiable at x equals 0. And we'll talk more about this in section 3.2, but I just wanted to introduce you to this concept earlier in the unit. Okay, let's take a look at the relationship now between the graph of f of x and f prime of x. And we're going to do a lot of this later on in the course, but again, I'd like to just introduce you to this concept early. So if you notice, the blue graph is my function. The red graph is the derivative of the blue graph. So basically, the red graph represents all the slopes of the tangent lines blue graph. And let's start at 1 on the blue graph. If I was to draw a tangent line at 1, it would be a horizontal tangent line, and that value is 0. And notice that the derivative is at 1 is 0. Now, any slope on this side of my curve is going to be positive, and they're going to get increasingly more positive as I keep going. And notice that my derivative continues off in a positive direction. Here, my slope is going to be negative and more negative and more negative. Notice to the left of 1, the graph goes further and further down. So looking at a function, you can sometimes quite easily identify the different points on the graph of the derivative based on the graph of the function. Again, here's another example. Here is my function on top. Here's my derivative. Notice here I have a slope of 0, and here I have an x-intercept on my derivative. Here I have a slope of 0. I have an x-intercept of my derivative. Here I have a slope of 0. I have an x-intercept on my derivative. In this region, my tangent lines are positive and my graph is above the x-axis. Here my tangent lines are negative all the way to there. In that region, the graph is below the x-axis, and we can continue on throughout this graph. But again, some more relationships to consider when you're looking at the graph of a function and its derivative. Okay, so that pretty much ends the first part, or it does end section 3.1. So there are some questions from both textbooks, so give those a try. And if you have any questions, you can check the answer key on the website.